thanks to the organizers of this conference for inviting me and giving me this opportunity to present some of this. The topic I'm going to present is in some sense an abstract topic, but I will try to make it so that I'll try to skip over a few details which won't change much of what I want to convey. And if you are interested in those minor omissions, then I can provide additional references. Okay, so how classifiable is my data? And before I actually get into this, I have maybe 3 or 4 foils which generally define what classification is. Now, this may be a repetition for some of you, but it just gets everybody on the same page, and so bear with me if you are familiar with this part. So what we are talking about is learning from examples, right? Learning from examples means that I'm observing something, and based on those observations, I'm trying to model an unknown system. And it is quite distinct from first principles types of model construction. So for example, I can use laws of conservation, maybe energy, momentum, things like that, to try and construct a model of some system. That would be a first principles based model, and that is not really what learning from examples is all about. And the reason why we want to learn from examples is that in many situations we don't know enough about the system, we don't know what the first principles are. And I've given you a very simple example here. We are trying to build this optical character recognition system. This is a very old problem. But I just want to show you the complexity of this problem. And forget the image processing part of it. Forget how we segment the characters so that, from a word we can get individual characters. Forget all of that. Come down to the situation where you have isolated each character, right? So from some handwritten text, you have isolated a character like this. And you want to recognize whether the character in your window, whether it is an A or a B or a C, right? It's a very simple task. Remove all the other complexities. If you just think of the several, possibly dozens of ways in which B can be written, right? And the dozens of ways in which A can be written, and the dozens of ways in which C can be written, it is exceedingly difficult to try and parameterize or try and come up with first principles that can distinguish between this character and A or C. On the other hand, if I know that this is a B and this is a B, an alternative approach is to try and build something based on this information and the fact that this is a B. Maybe I can construct a model which can tell me this and is much more easier to construct as well. So empirical models have an advantage, and they are attractive, especially when we don't know enough about the problem. Obviously, all the caveats apply. If you know enough about the problem, don't try to build empirical models, right? These are not solutions to everything. And if you know enough, then go with what you know. Okay, so here is a picture, and I think there are 2 or 3 more foils, and then I'll come to the central part of the talk. So what we have, another way of putting learning from examples is that there is some unknown system here. For the present, let's say that this is time invariant, and this unknown system has some input. It has an output which I cannot observe. What I can observe is that there is some observation noise that gets mixed with this, and I observe the output. So what I have with me is input, this part, and the output, which is this part. And based on that, based on these examples of input and output, I'm trying to construct this estimator such that the difference between what my estimator says and this system which I do not know about, that difference is as small as possible. And I'm using this error, the difference between my estimator output and the actual output, to adapt my estimator. Okay, so this is a different way of just putting this learning from examples. And to get us all finally on what I hope would be the same page, is this is the same example as before. This is B, and let's adopt a very simple principle that if the grid square has a black, whether partially or completely, we'll call it a 1, otherwise we'll call it a 0, or maybe the other way around. So if I have some data like this, I can obviously call this as 0, 0, 0, 0, 0, 0, 0, 1, and so on and so forth. I can do this row major scan and come out with an example. This is my first example, this is my first input. And the fact that this is a B, the output, the input and the fact that it is a B correspond to my example. And obviously I can pick examples from several people, from several different people writing it. So I have a whole data set. Okay? And what it is I want to do is to learn from this data, to construct something from this data such that if I am shown a B or an A or whatever, then I can say that it is a A or a B or whatever it might be. It's a very simple example. Obviously, you can take it to very complicated things. So, for example, this CMU experiment that was there, it actually tried to have a car driven by a model that was induced only from such examples. The examples in that case were that given, some inputs, which is the distance to, let's say, an obstacle or the curvature of the road and your present speed, what is your next step? Do you steer to the right? Do you brake? Things like that. And based on this construction, they could do it. Okay. And this is just for completeness. This is a 0-1 kind of situation. You could have situations where the data is real or complex or categorical and so on and so forth. This is fairly, I really don't want to get into this because this is not the central point of my talk. So, what I now want to pose the question, and obviously, you heard Professor Pal's lecture today morning. There are neural networks, fuzzy systems, Bayesian inferencing, statistical inference methods. There are many methods which can help you classify data. What do I mean by classification? That I can distinguish between A and B, or it might be a more complex situation. I can distinguish between things which are different from each other. The simple question I have, and which I think is a very important question, is the following. Obviously, this A and B that were there, they were in high dimensional space, right? Because the inputs, so if it was a 6 by 6 grid, you had 36 inputs, and it's in 36 dimensional space. So consider a much simpler case where you're just measuring two things. So I can plot it on this. And the training examples that I had happened to look like this. This is the only time I'm actually going to use the board. So I hope everybody can see this, right? So now my question to you is, these are two situations, right? And these are two separate problems. So focus on the first one, right? One of the classes is indicated by a circle, the other class is indicated by the square or by the cross. Right? And what is the purpose of, what is classification in this context? The classification is probably going to draw something so that everything on one side of it is one class, everything on the other side is another class. So this is one problem. This is some other problem which is also, there are also two classes, but the distribution of the classes is somewhat different. And the question I have is, which of these two is more difficult to classify, or which is a more difficult classification problem? Obviously, it is this right one, right? Because here I can possibly separate these two classes by a straight line, whereas here I would need a much more complicated curve to separate the classes. This quantification as to how difficult it is to learn something, this quantification does not exist in all of this learning literature. Right? There are some things that exist, and as I go, I will point those out. But fundamental question that I want to ask is, given some training data, how difficult it is to build a model? I'll just make one comment. You might wonder, why am I interested in that? I know how to make a model, so why should I be interested in trying to find out how difficult it is going to be? I might as well use that time to actually build it. The thing is that as we start making more complicated models, so right now the type of models we build, the type of neural networks or whatever we build, they are very simplified. There is a problem, and I somehow come up with the magical size of a model that will solve that problem. That is not really what we are after. What we want is that there is something, a much larger resource pool, and there is some level of resource allocation that happens when a problem arises. Okay? So the difference in the setting is quite, So that is what this talk focuses on, and hopefully I can show you some results which will be of use. So the way we want to, a more generic way of posing this problem is that there is some joint distribution. X is the input. So remember the input 0, 0, 0, 1, whatever it was. X is the input and T is the output or the target. So when I see a B, the target is that it is a B. So there is this unknown joint distribution, and based on some examples, I want to create this model T hat such that the probability that my model does not agree with the real or with the truth, that probability is minimized. Now, obviously, I've given some examples. Once I've created a model, I want it to predict, and therefore I want this probability over all x and t to be minimized. And the question again is, how difficult of x? Theta are the parameters of t. Okay. Now, there are a couple of things that are worth asking. One is that this T hat, this model or this predictor or this neural network or fuzzy system, whatever it might be, what actually controls its performance? So in the morning in Professor Paul's lecture, he pointed out several things that he had tried and he got good performance, or he reported on the performance that he got. But more generically, what influences the performance is that there is a non-zero Bayes error, in the sense that it is not possible, given the type of inputs that you have measured, it is not possible to completely distinguish between the two things, between the two classes or between the n classes that are there. So non-zero Bayes error, obviously Bayes error, if you knew all the class conditionals, is the lowest achievable error that is possible. So the decision boundary is in fact complex. This is the same as non-zero Bayes error. N is small. N is the total number of examples that you have. Uppercase N is the total number of, and that is small. You don't have too many examples. The dimensionality of those is very high. In other words, the data is in high dimensional space. And so obviously any estimation that you come up with cannot be reliable. So these are not very controllable. There is not much we can do. There are some controllable things, and that is the model complexity, and usually people try to tweak this to somehow or the other get performance out of it. Now, let me come to this part, which is actually the more relevant part to the talk. How good is a classifier? Now, why did I first tell you about what are the sources of error? Because there is a difference. Just because I constructed something which did not give me a low error does not mean that the problem is complicated. It might mean that what you constructed is not good enough, right? Or there was some problem with it or something else with it. So empirical estimates of error, meaning that you construct something and then you measure how well it is doing, is not necessarily a good way of characterizing the difficulty of the problem that is there. So how good is a classifier? There are these empirical measures that are there. You build the classifier, you use various statistical techniques, either sampling with replacement or sampling without replacement. You partition the training data into the training data and a separate test data. There are all kinds of variations, and you come out with these empirical measures. As I said, that is not a very reliable way, and secondly, it is computationally very expensive because you actually have to build the model in order to find out the error. There are some other approaches like VC dimension, which have been proposed. Now, with VC dimension, there is a different problem. The problem here is that, one, it is the worst case complexity, right? So the worst case complexity, and usually this worst case bound is a fairly coarse bound. Okay? In general, you would tend to do far better. Second, it does not actually depend on the given training data. So if I give you some data and based on that I ask you how complex is this problem, that is a different question to ask than asking how difficult it is to classify, to differentiate a sine wave from some other thing. So based on the given data, this doesn't address it, and it is there is also something called pack learning, which is probably approximately correct kind of learning. And here people often ask the question that is a concept pack learnable? Right? And once again, this doesn't really depend on the given training data. Right? It is more in the abstract that the question is being asked, that is this concept pack learnable? So what we want to do is to actually find out how difficult is it to construct the classifier given that particular instance of the training data. There are some other measures that are there which people use, to find out how complex it is. But once again, I don't think these are very good measures because the artifacts introduced by individual measures, somehow get mixed up with the actual complexity of the problem, and it's harder to say which one is which. So over the past 4 or 5 years, we have been trying to work on this and try to come out with a way of characterizing the complexity of a classification problem. And I'll show you some examples of that. And there were various techniques we came up with, and it turned out that the best one was actually a fairly simple one. So I'll just describe the one that turned out to be the best one with very nice properties and so on. So what we said was, or what I said was, that visualize an n-dimensional problem. So n dimension is the input space dimensionality. In other words, your inputs consists of n numbers, or n entities, maybe numbers, or they may not be numerical quantities. So visualize this in n+1 dimension using the class label as the n+1th dimension. So let me show you this picture. So supposing, just focus on the left part of the plot. So this is some training data that is given to you, right? These are circles over here, and these are pluses. So this is one class and this is another class. I hope you can distinguish. Now visualize this as so this is n dimensions, and in this particular case n is 2. So visualize this in 3 dimensions, where the third dimension is simply the class label. In other words, if the class is the circle, let's call it 0. If the class is this, let's call it 1. So all of these points stay on z is equal to 0, and all of these points become z is equal to 1. Right? Is this picture clear? Now, what would happen to this surface as the problem becomes more and more complex? So imagine, what does the surface, what does this surface look like for this problem? See, if I plot this in 3 dimensions using what I did over there, this would be on z is equal to 0, and then this would rise corresponding to these, and then this would be at z is equal to 1, right? So I would, in some sense, have a step function. Right? What would happen to the surface here? The surface here would be 0, and then it would be 1, and then it would be 0, and then it would again be 1. So the difference between these two is that the surface is far more complicated in this particular case than it is in this case. In other words, the one way I can substitute or an alias for the complexity of the classification problem is the smoothness of this surface that I have constructed. And if I could characterize the smoothness of this surface, then maybe that could serve as an alias for how complicated the problem is. Okay? So the smoothness or the roughness of the surface is a measure of the class. So how do I compute this roughness or the smoothness? Well, it turns out that there are, and all the image processing people, have been computing texture for several decades, and there are many very good methods of doing it. And we could use one of those, and the one that I'll tell you is a particularly simple one. A very small amount of, maybe I'll come back to this if required. I can skip it. So one way of computing the roughness of this surface is that if I have a point, let's say if the point is of some class, I look at the neighboring points around it, and I find out how many of the neighboring points belong to the same class and how many of the neighboring points belong to some other class. Right? And if all the neighboring points belong to the same class, then I can say that it's smooth, at least locally. Right? So if I sort of carry that a little further, we can define this sort of a co-occurrence type of a matrix. This is shown for two classes. And what this is saying is that assuming that a point belongs to class 1, class omega 1, what is the probability that neighboring points belong to class omega 1 as well? This is saying that given that I am class omega 1, I am a point, I am class omega 1, what is the probability that things around me are class omega 2? And similarly, vice versa. Right? So one way I can compute it very easily is that for each point, I take a neighborhood around it, I count how many, if this is of class 1, I count how many of class 1 points are there and how many of class 2 points are there. And the number of class 1 points add up here and the number of class 2. Or if that point happens to be a class 2 point, then the number of class neighbors add up, the number of class 2 neighbors add up here. Am I clear with this thing? And so you do that for all the points that are there, you know, adding it into this thing, and you will get a matrix, or in this case a 2 by 2 matrix. There are only 2 classes. If there were 3 classes, you would get a 3 by 3 matrix, right? Now, in this particular case, what would this matrix look like? For this particular case, this matrix would not have elements here and here, right? Or would have very, very small numbers in those off-diagonal entries. Why? Because close to a class 1 point, I have only class 1 points, right? Except at this border. And close to class 2 points, I have only class 2 points. Whereas these off-diagonal elements, they say that close to a class 1 point, how many class 2 points are there, right? So this off-diagonal entry is going to be small, or these off-diagonal numbers are going to be small, and this would be a diagonally dominant matrix. On the other hand, if you take a situation such as this, I will have off-diagonal entries as well, because close to a class 1, I have a class 2, and close to a class 2, I have a class 1. So, one way I can come up with a classifiability measure is that I simply add up the diagonal elements and I subtract the off-diagonal elements. And that is what is shown here. It is this plus this minus this minus this. And we term that as the classifiability measure. Now, obviously, you know, I can come up with any measure and call it a classifiability measure. For it to actually be a classifiability measure, it should have certain properties. And I won't go into those properties, but I'll tell you 3 properties that are there. The first property, which is actually the strongest property, is that for a given data distribution and when some conditions, so these are fairly mild conditions, I'll tell you about it. C1 is a fairly mild condition, C2 is a little bit harder to satisfy. But nonetheless, in practice, we often can roughly satisfy both of them. The sum of the classifiability measure as defined by this equation, right, the way we computed it. The sum of the classifiability measure and the Bayes error is a constant. So what that means is that estimates of how difficult a particular problem is, you know, to classify, estimates that I get from this measure are fairly reliable, right? Because after all, if the Bayes error is low, that means you have classified it. And if the Bayes error is high, that means then you have been unable to classify it. It turns out that, as I said, I've left out some of the intricate parts of this talk, but that there are three theorems you can state. This is the first one. The other two relate to the sparseness and to something called the boundary complexity. And you can state the same theorems for them as well. Okay, so let me summarize what has happened. So we have this measure, which does not require that I construct a classifier. Right? All I'm doing is I'm counting, which some of you might argue is sort of like a classifier, but if it is, then it's a fairly it requires fairly low amount of computation. So I have this measure now, and using counting techniques, counting which can be done in parallel if you so want, using counting techniques, I can figure out, or I can come up with a number which tells me how complicated it, or how complex it is to construct a classifier given that data. Okay. So, this is computing the proposed measure. I already described it, so I'll just skip it. This is just to show you on this axis is Bayes error, on this axis is classifiability as we measured it, and you can see that it is, the sum of this plus this is a constant, and obviously the lower the Bayes error, the more classifiable something is, and that is why this inverse relationship is there. There are multiple plots on this, and these multiple plots correspond to different neighborhoods. Remember what I said, that given a point, you look in the neighborhood to find out how many points of the same class and the opposite class are there. How large that neighborhood is, that is varied for these different simulations, only to show that this measure is not brittle relative to this choice of the neighborhood. So I'll show you two examples of how you can use these, and then I'll give you something which I think would be more useful if we really try to construct very, very complex systems. The first one is subset selection. The problem is very simple. I have, a large number of input variables, and I want to choose from those variables that are most relevant, right? And I want to discard the rest of them. So this is subset selection. And if I want to form some combination, linear or nonlinear combination of the input variables, then people often refer to that as dimensionality reduction. This particular case happens to be subset selection. So given some variables, I want to choose only those, or I want to retain only those that are actually relevant for me. So basically, you want to find something that is relevant to classification, and there are two things that are required. One is what is termed as a fitness criteria, and the second is a search criteria. What does it mean? What it means is that as I discard variables or as I include variables, I need some mechanism to tell me how good this particular subset is. So let's say I had three variables and I chose only two. There has to be somebody who tells me how good am I doing with these two, right? So that is the fitness criteria. The search criteria is that assuming I'm not doing well, I now need some other combination. Who gives me that combination, right? Who comes up with the subset, and that is the search criteria. So what people have typically done, or what the literature looks like right now, are based on branch and bound. And so forward selection means that you take one variable at a time and you stop adding variables when something, some information theoretic measure doesn't increase or doesn't change. Backward elimination is you sort of start with everything and you start deleting variables that don't influence the classification much. And branch and bound is sort of, you could say, somewhere in between. The two popular approaches that people have is this wrapper approach and filter approach. And what happens is, you take a classifier, using your search criteria, you come out with a subset. You construct this classifier, you see the error rate of the classifier. The error rate of the classifier is the fitness function. Okay? And if you try to minimize the error rate. So you take the fitness function, give it as an error signal to the search criteria, it comes out with some other combination, you reconstruct the classifier, and you keep on doing this in a loop. Obviously, the problem is that it is extremely computationally intensive to construct a classifier for each pass that is there. And if you had 2,000–3,000 variables, this can take up a significant amount of time. And the filter approach is sort of fairly similar. So what, since we have this way of characterizing how difficult a classification problem is, so you could very easily use it to do subset selection. How? You choose in the first instance that feature that has the most classifiability. And you do forward selection in the sense that after you have chosen it, from the remaining n-1, you add that feature which now maximizes the classifiability again. And you keep repeating the process till your classifiability doesn't increase. Okay? And that is all that is done. It is obviously very fast because we are not constructing this classifier. We are only coming out with this classifiability measure, which is a simple counting technique. And it is as accurate as the wrapper approach. So I am not sure if this is fully visible. The wrapper approach is somewhere here, and the proposed or the classifiability based approach is somewhere here. These vertical bars are one standard deviation. So you do this many times, and this gives you sort of a numeric look at the thing. So these are very well-known data sets from the UCI machine learning repository. And this data is in 59 dimensions, and the digit data is in 649 dimensions. So the digit data is sort of similar to the A and B example that I was using. And what we said was that only select 2 features from those 59 features and only select 10 features from these 649 features. And this is the features that were chosen by the classifiability measure, feature number 12 and feature number 16. And these were the features that were chosen by the wrapper approach. So there are 2 ways to do this. One is that you fix the number of features and you compare the accuracy. The other is you let the other one add as many features to get to the accuracy that you have. Okay? So this is with 11 features, it reached roughly this accuracy. The more critical thing is that the time taken is significantly smaller in this case as it is in this particular case. So this is about half. This happens to be much, much lower. The accuracy on the full set, in other words, if you used all the 59 features for the sonar data, is this. And if you use the subset, in other words, only 2 features, the accuracy is about this. So accuracy actually increased. And if you are surprised with that, then you should not be, because there are certain classifiers which are very sensitive to irrelevant features. So for example, the nearest distance or the nearest neighbor classifier is very, very susceptible to irrelevant features. The irrelevant features at distances in your nearest neighbor computation. Okay, so this was one example. Here is another example. So I want to do decision tree induction. And decision tree is fairly straightforward. Given the data, I choose a particular variable, and based on some value of the variable, I split the data. And then at each of the nodes, I split it further, and I keep doing this till I come to leaf nodes which are fairly pure, which have only data of one class. The problem with decision trees is that it is a very greedy approach, in the sense that the decision that you make at a node is based on a local search, and therefore a particular split that you do might result in a partitioning of the data that is very complicated to partition later on. So let me give you an example. So this is some data that is there, and there are two classes once again. This is circle and this is plus. So the first node, the root node at which the decision was made, and this is using some variation of ID3 or ID4.5. So it is trying to use entropy as a way of finding a partition. So this is the first partition it found, because this results in the maximum reduction in entropy. It is not hard to see, because once you partition this space with this, all of these are one class, and there is some impurity. On this side you have both the classes, but this side is relatively pure. The second one, now notice what happened. Because you partitioned it this way, because you are doing a local search, at this point, this partition gave you the maximum reduction in entropy. However, it left a partition on this right half plane. It left a partition which is very complicated. And it had to create 3 additional nodes. This is the second one, this is the third one, and this is the fourth one. It had to create these 3 additional nodes so that it could classify all of this data correctly. Okay? So if you know something like a classifiability measure, what you can do is, rather than just basing the split decision on entropy or something like that, you could base it on the node splitting criteria plus the classifiability criteria, because the classifiability will tell you, or what this modified cost function will tell you, is how well I'm splitting the data here, and how classifiable is the data in this partition. Okay, so in some sense, you can build look ahead using a measure such as this. And that is all I'm saying here, that you can use some kind of a gain or some information theoretic criteria here, like entropy, and the classifiability measure. So find me a partition that results in the maximum decrease of entropy and also leaves each of the 2 partitions classifiable. Lambda is something that just adjusts the relative weightage of the 2 things. And this is not very relevant, over several data, obviously it's doing well, or else I won't be telling you. You could look at some, I'll give you some things to, some papers in which the simulations are described. So the reason I'm also skipping over it is, any empirical, it's very easy to come up with data that can make it look very good, right? I mean, there is always this theorem that floats around, that for every algorithm there is a data set that you can invent on which it does very good, if not the best. So, it's not really relevant. There are some properties that we have derived which says that it should do well. So, I haven't really covered on one part of it, which is this part that we have been working on now, which is, assume that we have a large model at our disposal. Is it possible to sort of break out small parts of this large resource and focus it on problems that arise, and the size of that chunk you break off depends on your estimate of the complexity of the problem. So in other words, you're sort of doing self-organization along with trying to solve whatever that problem is. So I haven't covered that part of it. So if you want to read some more, there are some references I have given here. I haven't given any of the newer references since they get into some different issues like automatic resource allocation in learning systems and all that. But most of them, I should point out, these are all my students who are who finished around that time, or near around that time. Okay, so that's all I had to say. There are many very basic problems that remain in learning theory, and one of the most basic problem is, what is the I'm trying to learn something. What is the complexity of what I am trying to learn? Okay. And if we can answer this question, it has very, very, very basic implications. So that's all I had to say.